Office hour, week 6, about the water potential. AP Biology, unit 2, but I can't recall which section is that, but it's all about the water potential. So before we start with the water potential, let's talk about what is really tonicity. We have a beaker, and when we add sugar molecules in here, these are going to be the sugar molecules. These are called solute. So they are the solutes. And we have the water particles in here. That's the solvent. And altogether, solute and solvent makes the solution. We distinguish between hypo, hyper, and isotonic solution based on the solute concentration. So through example, if we have a beaker, 3 beakers, and I will have 10% sugar, glucose in here, and 20% glucose in that solution, and 30% glucose in this solution, I can say that the 10% glucose solution is hypotonic compared to the 20 and the 30% glucose solution. Hypotonic because the solute, it's all about the solute concentration in the solution. Can I say that the 20% glucose solution is hypotonic? May I say that? I would say at this point, think about the relative relationship between other solutions. So we cannot say that this is hypotonic. Hypotonic only to 30% glucose solution. But I can say this is hypertonic. It contains more solute than the 10%. So I can say this is hypertonic compared to the 10% solution. So the tonicity is relative. We can say that 30% is hypertonic to 20 and 10% glucose solutions, but we cannot say that is hypotonic unless I would draw a 40% glucose solution here, and I would say, yes, that is hypotonic compared to 40%, but there's no over there, so I cannot just do that. So that's about tonicity, and we will get back to it a little bit later. Okay, so let's take a that has a semi-permeable membrane separated the water between the tanks. So this is water in here. The water molecules, I will draw 10 water molecules on each side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And in here too, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Representing the water molecules. Let's add solute to each of them. The solute, again, sugar or sodium chloride, doesn't matter. I will add 4 of them here. 1, 2, 3, 4. And I will add 1 sugar molecule, this is glucose, let's say it, to that side of the tank. This I will call side A and side B. The membrane is semi-permeable only for the water, but not for the glucose. What can we say about tonicity-wise A and B? Tonicity-wise, remember, relative to their solute concentration, we can say that B has more red dots, that's the solute. So this is hypertonic. And this one has only one dot, so it's going to be hypotonic solution. Now we will examine the water movement in here. I would like to point out that the solutes are forming a hydrogen bond or bind one of the water molecules, bind weakly the water molecules. So in this case, we want to see the number of free water molecules in each segment, each side of the semi-permeable membrane. And those are the molecules that can go, those free water molecules are the ones that can cross the semi-permeable membrane. When they are not free binded water molecules, they cannot cross the semi-permeable membrane. So let's see how many free water molecules we have in A. 1, 2, 3, 4, 5, 6, 7, 8, 9. So in here, 1, 2, 3, 4, 5, 6 only. So we can say that the water moves from high concentration, free water concentration, to a low free water concentration. So the water will move from A to B area through the semi-permeable membrane. What do we say? The water will move from a hypotonic to a hypertonic place. Or we can say water moves from high free water concentration area to a low free water concentration area. So both of the terms are correct. Getting into any, please let me know if you have any questions about that. No. We 3 containers. And each of the containers have a solution in them. And we place one cell in each container. This is a cell, that is a cell, that is a cell. In a scenario, let's say we have tons of solutes outside and only one solute inside. We can say that the outside is hypertonic. This is hypertonic relative to the cell. And in this case, the water will move out from the cell because water moves from hypo to hypertonic area. So what happens with the cell, if it's animal cell without cell wall, it will shrivels up. Shrivels up. It crenates. It crenates, it will be smaller. Also, in the plant cells, we call it plasmolysis. The cell shrinks, the cell wall will stay the same, but the cell membrane get detached from the cell wall. So the cell would look like something like this. for the plant. This is the nucleus from for a plant cell. What happens in here? Let's say I have 3 dots in here. I have 3 dots in here. So isotonic solution in both cases. Iso means same. The tonicity is same. So as much water leaves, as much water goes in. Nothing will change with the animal cell. The plants, they are fine with that too. The last scenario is going to be, this is so the B and the C is, let's say we have tons of dots inside of the cells as solutes and very few dots on outside. We say based on the solute concentration, the outside is hypotonic relative to the inside of the cell. In this case, the water will go inside of the cell because water moves from hypotonic to hypertonic area. So the cell, animal cell without cell wall will lyse. This is burst. Will burst the animal cell. The plant cells, they love this state because they have a high turgid potential in here. They love living in a hypotonic area. They will not pop because they have the cell wall around them. So that's all about the tonicity. And let's get into the calculation. Calculation part, water potential. That will be the second half. Water potential. So water potential is the pressure potential plus the solute potential in a closed system. The best way is, so the pressure potential, if it's a closed system and pressure builds up in the cell or in a container, and the solute potential gives a potential for the solution to decrease its water potential. Distilled water's potential is 0 in an open container. The potential is always negative. So through an example, we have a cell in here. Okay. And the cells, let's say, pressure potential, pressure potential is going to be minus 3.5. I came up with the number bars. This is a pressure that builds up inside of the cell. And based on its solutions, the solutes in the cell, the solute potential is going to be minus 2 bars. The water potential of the cell is going to be minus 3.5 plus 2.0. So it will be 2.0. It's going to be 5.5 minus 5.5 bars. Excuse me. So minus 5.5 bars. Water potential is always negative or 0. That's all. Number 3 in here, let's discuss one thing. If the outside of the the soil's water potential, we want to figure out the soil's water potential that this cell is. Let's say this is a root cell of a plant. So the water potential of the soil, it's pressure potential plus solute potential of the soil. There's no pressure because it's not in a closed container, so it's going to be 0. This for us. Now, the water potential of the soil is going to be 0 plus solute potential. You can get it from the AP biology formula sheet, is minus IC minus ICRT. The I is going to be the ionization constant. For glucose, it's 1. For sodium chloride, sodium and chloride 2. For magnesium chloride for calcium chloride, CaCl2, Ca, calcium chloride 2, so it's 3. This is the ionization constant. So the C is the molar concentration. The R is the pressure constant, that is 0.0831 with a bunch of letters, liter times bar per mole per Kelvin, and the T is temperature in Kelvin. So 0 Celsius is 273 Kelvin. Kelvin. Okay, so let's say that in the soil, the salt concentration is going to be 0.1 molar sodium chloride. And the temperature is going to be 20 Celsius. That's the best to use that. So we'll plug the numbers into equation. The I, because we are talking about sodium ion, it's 2 ionization constant, 1 for sodium, 1 for chloride ion, so 2. The concentration is 0.1 molar times the R is the pressure constant. This is 0.0831 times the temperature is 20 Celsius. 273 plus 20 is 293. And when you do this whole calculation, we figure out that the water potential for the soil is going to be minus 4.86 bars. So the application comes here. The cell's water potential is minus 5.5, and the soil's water potential is minus 4.86. The water always moves from high water potential to low water potential. Minus 4.86 bars is a higher number because it's negative compared to minus 5.5 bars. So in this case, the water moves into the cell because the soil is hypotonic compared to the cell, as well as water moves from high water potential to low water potential. This is scenario 1. I will move a little bit like this for scenario 2. Let's say some people are using salt to melt the snow from the pavement. So the salt concentration, let's say the C is going to be not 0.1 molar sodium chloride, but they use salt and it will be 0.2 moles of sodium chloride to melt the snow at winter time. Now, again, the water potential of the soil will be still, there's no pressure potential because it's open. So, but the, so it's 0 point minus 2, the ionization constant, times 0.2, because this is the molar concentration, times 0.083, that's the pressure constant, and the temperature is the same, 20 Celsius later on at springtime. So 293 Kelvin. And altogether, if I do the calculations in here, I will get minus 9.74 bars. Now, this is my answer for the soil's water potential. Now, water always moves from high to low water potential. So the water potential of the cell is minus 5.5, and I have minus 9.74 bars for the root. Which way would the water go in that case? It moves from high. This is higher number because we are negative, and this is very low number. So for that scenario, the water leaves the root cell. Water will be very important for photosynthesis. Later on, we will just learn about that. Water is super important for that. So in this case, that plant would die because it will not be able to absorb water into its roots. So that is why water potential is important, and we can really calculate out. And the calculating out the water potential helps you to figure out which way the water will go. Okay, when the outside and the inside is the same, they are isotonic relative to each other. So as much water goes in, as much water goes out. And that's it about water potential and tonicity and the free water molecules. Hope that this recap really helped you guys. Have a good day. Bye.